question is a reference that when we push these electrons around and we end up showing the negative charge showing up on that last carbon, I was then saying that we could show that then come over and attack the other structure. Where it hooks up on the other structure is again dependent on resonance. And I'm going to color code this as a mechanistic arrow versus a resonance arrow. So we'll call our mechanistic arrows purple and our resonance arrows I'll do it blue.
Okay.
This can push up and come around, which then leaves a very large partial positive on that last carbon, which is why we would then suggest that what's happening is that it attacks in here, okay, or it favors that carbon. What you're, I believe, referencing is that you notice that if you draw out these resonance structures, the oxygen becomes negatively charged, the nitrogen becomes positive. Why don't we see it link up there? Okay. The reason is how we're going through and overlaying these things. We're using We're using the resonance to determine how the Diels-ALder mechanism works. So the resonance is favoring certain positions to activate the Diels-ALder reaction. Okay. The Diels-ALder reaction is still our pi bond coming across, the other pi bond attacking, and that pi bond shifting over. Okay. We're using the resonance to see how the charges fall within that six-membered system to decide how it's going to force the regiochemistry of all the substituents. Okay, so the resonance isn't driving the reaction, it's driving the arrangement of the pieces around the reaction.
Okay.
Does that kind of make sense?
Yeah.
Close enough?
Why does that still happen when there's all of these other little guys hanging out that could react or don't react or should react? Or
What I would suggest is that those extra pieces, well, there's so many colors on there, I'm not sure I can draw anything else, that are extra pieces out here are ultimately affecting an individual reaction. Why do they not go through and do their own reaction? They could potentially. But in the case of this, the overall reaction, or the primary reaction that occurs, is our Diels-ALder reaction. Okay, that just happens to be the favored one because of the thermodynamics, the energetics, all you want to go through. Are there other products that could go through and happen where those other pieces do something else? Absolutely. That is a possibility. But in the overall scheme of this reaction, when we run it, we can control it with temperature and other things to limit those other products. So if you looked at an actual experiment, everybody, particularly when you write up a report, you're like, oh, I didn't get 100% yield, that must have been awful. Well, that's one of the things we're trying to bring in this semester is that most reactions won't give you 100% yield, okay? And that loss of whatever that extra percentage is could very well be something else happening up in that orange box. Those things doing extra weird chemistry. Unfortunately, we can't control that as easily just because of what we really have access to as chemists, okay? So we can really look at the predominant products, the major products, whatever we can get a hold of to actually analyze. The stuff that happens in that 10-20% range doesn't happen in high enough concentrations to allow us to easily isolate it, or in even more of a potentially skeptical argument, doesn't give us a high enough amount of it that we would care to even evaluate it because it's not taking us someplace that we want to get. So when you go into the lab, you want 100% yield. So you want whatever's going to get you the highest percentage. The other stuff that's happening up there, could it potentially do other things? Yeah. Okay. Is it? Quite possibly as well. In the case of the Diels-ALder reaction is so energetically favorable enough on its own that we can add in a bunch of other functional groups that usually, even by adding that chemistry, doesn't change that we're doing the core Diels-ALder reaction. It just changes how the Diels-ALder reaction occurs.
okay.
Does that make a little bit more sense?
Yeah,
I know, it's very hand-wavy, but I think that's about the best I'm going to get out of that one.
yeah, that makes sense.
This is a lab question. Upper right-hand corner, we got the structure of maleic anhydride. Okay, and the question asked is, why is maleic anhydride a bad reagent to do? It's not going to allow us to decide which mechanism is valid. Okay, so it's a bad structure for this. Well, to decide which mechanism is valid, what are we ultimately looking at? And yes, that answer is kind of up here. Yeah, the products. What we're looking at for a DA1 is we would expect 2 products, and for the DA2, 1 product. So simultaneous versus concerted, or stepwise. Okay? So let's go through and take a look at the stepwise one. For us to get two products, what had to happen? So we look at the mechanism as I got outlined up there. What had to happen that was different in the DA1 than in the DA2?
Our bonds had to break and then we had to make a carbocation.
No.
Isn't it the how it attacks, I mean, how it actually comes together and forms? And you end up with two different products because there's two possible.
No, so the two possible attacks, an up versus a down, happens in both mechanisms.
Okay.
That's valid in both.
Okay.
The real key difference is in the sigma 1, if we take a look at that first step, we end up with only one sigma bond in back, and we've lost the pi bond in the dienophile, because it's now an anion. Okay, so what we're looking at is right here.
Because when the bonds break, it doesn't happen all at once.
So we lose that pi bond and it becomes the anion, but what we have now connecting our old diene is a sigma bond that can rotate. That free rotation allows for the exchange of the location of A and B, which is why we get two products. Okay?
But
So
in the other, because it's happening simultaneously, then there is no rotation.
it can't
at all.
rotate.
It can't rotate.
So
A pi bond is formed.
our
there's no rotation.
mechanism differences are ultimately all hinged on that sigma rotation. If the sigma bond rotates, if we can find evidence of that, we're looking at a DA1 mechanism. It's stepwise. Okay? If we see no bond rotation or no evidence of a bond rotation, we would consider the concerted mechanism, the DA2. Okay? So that's the evidence we're hinging on. We want to look for those two products.
Okay, when you say see, if you're in the lab, okay, I mean, I'm trying to visualize this here, okay? When you say you're seeing something or whatever, you're not seeing something, you're observing something.
You're observing, so I'm trying to track
Right.
down where the C was objectionable, which is okay. What we're observing as a possible sequence of products.
Okay, but that's what I'm saying, okay, is it gonna be a sequence of product or is it gonna be a single product?
So in this,
In
this
situation,
circumstance,
right,
if it
we
was
have-
DA1,
It
we
would
would
be
observe two
products.
products. In
It's
DA2,
it's
one product.
Okay, so that's not,
Yes.
what I'm saying is visualizing that and saying, okay, I'm in the lab. If I see one product, then I know that it's DA2, right?
Yes.
Okay, so there's no question as to whether or not it's DA1 or DA2.
Well, yeah, so that's the point. The
Oh, okay.
experiment would give us
Okay.
the result
Okay.
to say it was one or the other.
If I saw it, well, duh,
Yeah,
then I'm
so-
gonna know.
Well, yeah, but you go into the lab saying, I think it's one of these. I
So
want to look
we're
at my
making a
result.
prediction. We're making
Yes.
a prediction that it's gonna be DA1 or DA2.
Yes, that's the idea.
Based on what we're utilizing for the experiment. Is that?
Yes, so what we want to do is design our experiment such that we can see a difference between these, DA1 versus DA2.
Okay,
And if the reagents we use prevent that sigma rotation, that's a pretty
Then-
useless experiment because we
Right.
can't make any conclusions about it.
sure, sure.
Okay? Or if the reagents we're using don't allow us to see a difference even if we had two products.
Sure.
For instance, if we just had carbons and hydrogens on it. Well, sure, we could have two products, but I have no way of observing that result. So what we're hoping to see is that if we had DA1, we would end up with two possible products, and those two products would be characteristically different enough that we could identify them.
Okay,
Or see that there were two products.
okay,
Observe. You're not really seeing.
right.
Find the
We're
evidence for
Right, yeah.
two possible products. Okay. So if we go back to the classic Diels-ALder experiment, it's cyclopentadiene and maleic anhydride. Okay. And the argument that I'm putting forth in that question is that maleic anhydride is an awful choice to try and determine between these two mechanisms. Okay. If we want to go in and just say, oh, it's DA2, as we, I guess, now already know the answer officially, it is a concerted mechanism, then we don't care what we use because all we're going in is saying, it is this, yeah, we just proved it was this. We just did a reaction for the sake of doing a reaction.
Doing a reaction,
What I'm
not determining
not
whether or not
trying to learn from what the
Learn
reaction
the
is.
Diels-ALder
Yes.
principle.
So that's why I object to the maleic anhydride experiment, because I don't think that reagent sequence allows you to distinguish between these two. So that's what the question's asking. Why does maleic anhydride not allow you to distinguish between these two? Well, what allows you to distinguish between the two? The primary issue. We have to have that
It's
sigma
bond.
rotation.
Yeah.
Okay? Where is that?
There is no sigma rotation in maleic anhydride
Because it's a
already
ring. There is no way to rotate about that bond because it's already locked in
It's
place
already locked
because
in
of the
place,
ring.
So there's no rotation.
Exactly right.
And there's
So
no possibility of any other product.
as
then you're
well
single
as
out.
far as are these two mechanisms go,
Sure,
the sigma
using
DA1
those
or
two together.
DA2, exactly right. We could do a different issue, which is the next part of it, endo versus exo, and that absolutely will still show up with maleic
Sure,
anhydride,
sure.
but it doesn't address the difference between the mechanism possibilities.
Okay.
Also, I was about to ask, how does this factor into endo and exo?
So endo and exo, if we go all the way,
One product.
when we get into the endo and exo situation, that was here with the maleic anhydride. So this is the experiment that was outlined for you.
Okay.
Okay, and we said this was a bad experiment, we're going to change it. We went through and said, we don't like this whole sigma up, sigma down thing, so we're going to get rid of the sigma up option by using the cyclopentadiene, because now that bridge carbon blocks the sigma up.
Okay.
Okay, so that was the whole point. This orientation, we can't get the sigma up product, it's not going to happen. Okay, in this orientation. But that brings up the next question. Is there another orientation that we could have brought the dienophile in with?
Yeah.
That's where we rotate it. And instead of having the maleic anhydride oxygen aimed towards the diene, we have it aimed away from the diene. We end up with the exact same two products that we
Because
had
you can-
in the previous
you can
situation.
flip it.
You can move
Up
it
or down.
down.
Exactly right.
So,
So,
can you get both an endo and an exo?
so endo and exo are still possibles. So
Okay.
that's where we run into now the question of, okay, which one do you actually get? Right, so when you go through and do the experiment, that's what you're going to end up seeing, is these two structures have drastically different intermolecular forces. One is all balled up and one is very flat. Okay, well, if you change the overall structure, you're going to change how it interacts with other structures. Melting point changes, boiling points change. So if we get the endo product, we expect one melting point. If we get the exo product, we expect a different melting point.
Oh, absolutely.
Okay? That allows us to then go back and say, oh, when we ran this experiment, we got the DA2 mechanism and we got the endo result, which matches what we would have expected. Ideally, you would have done the experiment before we talked about all this, but that's beside the point.
Now, how does,
Did you just, wait, repeat what you just said?
That's what Sarah, okay, let me try. At the end of the experiment, what you will in theory prove, hopefully to yourself, is that it's the DA2 mechanism, concerted, and we get the endo product. So you get those two primary results out of it that you then go back to everything we just lectured on and say, oh, that matches everything that we were told in lecture. Look at that, Mike was so smart, he knew the answer. Right? Ideally, what would have happened is you go into the lab, you come up with the DA2 mechanism, you come up with the endo preference, and then we go through and review why. That would be the lecture part. But because of timing and overlaps between when you can be in lab and when we're in lecture, can't really do that. So what we end up learning in lecture, in this case, comes after or came before what you learned in lab. But the lab is still being designed with the intent that you're trying to mirror and self-discover everything that we're talking about in organic chemistry. All of the rules. How do we get the Diels-ALder mechanism? Someone went into the lab and set up an experiment to prove it. How did they find out about endo versus exo? Somebody went into the lab and set out to prove it. Okay. That's kind of what I'm trying to build out of this assignment and trying to get you guys to think about and see. I also have to come up with questions to quiz you guys and see, like, is that how what you feel came out of this experiment? So we'll see what happens with that.
Now I have 2 questions. I think I might have switched this in my notes. The endo is the kinetic.
Yes.
Okay. And I didn't switch it. Now, when we're doing the melting point, should we know the melting point, like the theoretical melting point of
I
our
don't know.
product?
You tell me. Would you know you have the endo product with just a melting point, with nothing to compare it to?
I wouldn't know
So yeah, you should find the theoretical melting point.
for both of them.
Yep.
And if we get something split down the middle, we can assume we got like both.
You,
gotta make
Does it tell us what our product is going to be?
I don't officially tell you what the product's going to be either. I was
Well,
kind of
then how am I
like that.
supposed to know? I'm supposed to come up with the,
So I'm
what
gonna
I